during the times of, on this picture that you can see here, what I'm calling cosmic dawn and the dark ages. So the dark ages, there are no luminous sources particularly, but there is neutral hydrogen. So eventually we might be able to map the neutral hydrogen during those periods, but then the first properly luminous sources switch on, the first stars and galaxies, we call that time cosmic dawn. And as they switch on, they start ionizing the neutral gas around them. During a period we call reionization. The universe flips from being mostly neutral to mostly ionized, and with the 21 centimeter line, we can see the regions that are still neutral, and so you start seeing essentially bubbles developing. So you can see that in this little picture here. You start seeing gaps in your 21 centimeter distribution as ionizing sources switch on. And so we can use the 21 centimeter line to probe the kind of large scale properties of the intergalactic medium and measure things about how this reionization process is taking place. And of course, this has massive implications for theories of galaxy formation and evolution. So beyond that, I've mentioned the dark ages, cosmic dawn, reionization. There's still neutral hydrogen around at low redshifts, late times, but most of it should be sequestered in quite dense, what we might call damp Lyman alpha regions at lower redshifts, where it's protected from this UV photon background that exists at late times that would otherwise ionize it. And so we can actually see, we can do resolved studies of neutral hydrogen in individual galaxies if they're quite nearby, and I know some people in the audience are very familiar with that. But we can also try and measure essentially the signal from all of those galaxies or a large number of galaxies in some region. So kind of essentially pixelize the sky and measure the total intensity of all the neutral hydrogen in quite coarse grained pixels, and then make a map of the large scale structure. So instead of looking at individual galaxies, we can kind of make a somewhat lower resolution map, but which follows the large scale structure of the universe, and which we can use in a similar way to how people use galaxy surveys, so as a probe of the underlying dark matter distribution. So types of radio telescope. Sorry, I'm actually going to try and... There we go. Sorry about that. Types of radio telescopes. So I'm actually going to talk about what I think are the kind of two main configurations of radio telescopes that you might want to do intensity mapping with. So the first one is the simplest, I guess, which are the single dish telescopes or autocorrelation mode. And that's where you have one or possibly many dishes and you operate them independently. You don't correlate the signals between the dishes. You just detect the total power from the dishes. The resolution depends on the size of the dish, so roughly it goes like lambda, the wavelength, over d, the dish diameter. That gives you your angular resolution. And in general, you want to scan quickly across the sky to beat down something called 1 over f noise, or correlated noise, which is in effect mostly in the receiver gains. These things can be very highly sensitive, especially if you have a large dish, but the calibration has this 1 over f problem. You have to be quite careful with how you calibrate these things, especially if you're very rapidly scanning across the sky. You have lots of time-dependent effects that you need to worry about as well. Alternatively, you can build an interferometer, and this tends to be the more popular approach. So you can connect many dishes together, and then you cross-correlate the voltage signals from those. So cross-correlate an average, and you get visibilities. You can measure visibilities, which are a kind of a sort of proxy for measuring particular Fourier modes on the sky. The resolution now depends on the distance between the receivers mostly, rather than the size of the dishes or reflectors themselves. And interferometers tend to be much more stable in a single dish telescope. In fact, you can even run them as drift scan telescopes, where they just sit staring up at the sky. There's no movement. But they have much more complicated spectral characteristics. There's a lot more frequency-dependent effects in them because they're interferometers. Here's a kind of overview of some current experiments. I've been quite selective. I've only chosen a few. But you can see some of the kind of variation in the way these things are designed. You can see some individual dishes in the top left. I think the one in the top right is chime, which is all of these kind of half pipe kind of cylindrical reflectors with rows and rows of receivers on them. The middle one, C, is actually HERA, quite an old picture of HERA now. You see we've got lots of individual dishes, but they're closely packed together. On the right is MWA. You have these kind of spider-shaped dipole-type antennas. Tianlai in the bottom left. That's a kind of combination of dishes and these cylindrical reflectors. And then you can see LOFAR in the bottom right, which is bunches of dipole-like receivers. The point is that there's a tremendous diversity of these experiments. There are many ways of trying to measure the same signal, and each design has pros and cons. And the main limitation at this point is data analysis and being able to analyze the data and actually calibrate these telescopes in to an extremely fine level of precision, so that we can actually measure the 21 centimeter signal. So there are lots of experiments out there. They're all taking measurements and getting really interesting science out of them. It's just we can't quite reach that 21 centimeter signal yet because of this complexity of the calibration challenge. So the two I'm going to focus on today, because I'm personally involved in them, are MeerKAT and Hera. So again, this is a slightly older photo, but it's from the air, so it gives you a sense of the kind of scale of these things, and the fact that conveniently for me, they're on the same site. So this is the SKA South Africa site in the Karoo Desert, where the SKA-1 mid, the mid-frequency dishes will eventually be built. MeerKAT will actually be part of the SKA-1 mid array. So you can see at the top, you see all these dishes, the MeerKAT dishes scattered around this semi-desert landscape, and then Hera is tucked away in a corner nearby. So Hera is actually considerably more constructed than it looks in this picture now. That picture was taken a couple of years ago, and we're quite close to having 350 dishes, whereas MeerKAT has been operating for a few years already with its full set of 64 dishes. I think it's nice to see an aerial photo and you can see them together. So, the tyranny of dynamic range, what do I mean by this? I think this is the big problem, really, that we're all trying to solve. So why is 21 centimeter intensity mapping hard? And I've already mentioned it's because the fluctuating 21 centimeter signal, this signal from structure, variations in the brightness temperature of the 21 centimeter emission, which correspond to variations in the density of dark matter, ultimately, at late times, or the ionization state of the IGM at earlier times. Those fluctuations are really small compared to pretty much every other source of radio emission. So if you look at this plot here, you can see I've got a brightness temperature on the y-axis and just observed frequency on the x-axis. This is a simple simulated signal, and the mean H1 signal is this black line. So you can see here it's kind of at the milli-K level. There's some uncertainties in that. And then you can see fluctuations around that. That's this the blue line, and we've just chosen one particular line of sight. The fluctuations will be different depending on which direction the telescope is looking in. And I'll just point out this frequency range is mostly the late time frequency range. So redshifts from about 0 up to I guess 6 or 7, something like that. And then on top you see the foreground, this red line. There's a little bit more structure in the foreground than this gives away, but a power law is not a bad guess at what these look like. And you see how many orders of magnitude there are between them in brightness temperature. The foregrounds are incredibly bright, but hopefully much more spectrally smooth than the H1 fluctuations, which are very spectrally unsmooth, but just very faint. So we hope that these two signals are very well segregated in frequency space. You've got very bright but very spectrally smooth contributions from the foregrounds, and faint but rapidly fluctuating signals in the 21 centimeter sector. When you run this through the response of an interferometer, however, you get quite a nasty effect that normally we call this the foreground wedge. And essentially, because the response of the interferometer has its own kind of complicated spectral form, it modulates those nice, spectrally smooth foregrounds and kind of chops it up in a way that depends on the length of the baseline. So that's on the x-axis here, the length of the baseline that you care about. And what happens is that modulation essentially scatters some of that nice smooth structure, which would be at very low Fourier modes. In this case, we've taken a Fourier transform along the frequency axis. We'll call that delay, tau, for reasons I'm not going to go into if you're not already familiar with that. So tau of 0 means nice, perfectly smooth. That's a 0 or DC mode in your Fourier transform. And as you move away from tau of 0, you're looking at shorter wavelength fluctuations in the frequency direction. And so you can see, as a result of this modulation effect due to this spectral response of the interferometer, as you go to longer and longer baselines, they're more and more chromatic, so that they have more and more spectral variation, and they essentially scatter this, what would be this nicely segregated, smooth, spectrally smooth foreground contribution to much higher values of tau, so much shorter wavelength Fourier modes, essentially, or higher K-parallel Fourier modes. And it forms this characteristic wedge shape, and depending on the shape of the reflector you have, that can help suppress some of this modulation. And so you can see the difference here, but this is a simulation study, but the difference between a dipole and a dish, for example, you still have this wedge, shape, but the bits inside the wedge might be suppressed a bit more. The point is, because interferometers particularly have this quite complicated spectral response to what they're measuring on the sky, there's a bunch of Fourier modes, particularly as you go to longer baseline lengths, that are essentially just blotted out by these bright scattered foregrounds. So you can try and undo the spectral response and model that spectral response of the foreground and put that foreground power back where it should belong, close to tau equals 0, or you can just avoid this wedge region altogether, give up on it, and just focus on Fourier modes well outside the wedge. HERA, which I'll be talking about, takes that avoidance approach at the moment. We don't try and model the foregrounds too much. We have to do it a little bit to get our calibration, but we're trying to just see stuff outside the wedge for now. Okay. So there are other effects, other systematic effects that are a problem as well. This wedge one is kind of the most eye-catching, but there are a bunch of other systematic effects, things like cable reflections, which can introduce spurious spectral structure, mutual couplings between the receiver elements, all sorts of stuff like that. And another systematic effect comes from how you do the calibration. If you do your absolute calibration, to get your absolute temperature scale, for example, and to do that, you need a model of the sky essentially to set the 0 level. If your model of the sky is incomplete, that biases the calibration, and it doesn't just bias it by a constant amount; it may also bias it with some amount of additional spectral structure. So you end up not doing as good a calibration as you need, and you end up again with power scattered outside the regions it should be constrained to be within. And then there are other effects too, additive effects. So especially radio frequency interference, you get spikes or low-level additional power. You get signal loss when you start averaging together data that has calibration errors. Statistical signals that should be adding up coherently end up cancelling out slightly because of those calibration errors, and you get a bit of destructive interference and you lose signal. Also, when you start filtering things out, like foregrounds or other systematics, you're removing signal as well. Okay, so that was the introduction bit. Hopefully I didn't go over that too quickly or too slowly, and I'm always happy to answer questions about that stuff. But next, I think I'll move on to the preliminary HERA upper limits. So there's a nice picture of HERA in the desert at sunset with a nice purple sky, as you can see. So I quite like that picture. But here's one in the day where you can actually see some details. So what is HERA? HERA is a mostly US driven experiment out of the University of California, Berkeley. There are lots of other universities involved, including Queen Mary. in the UK, and the actual site of HERA is the SKA South Africa site. And the instrument itself is a bunch of essentially 14-meter diameter chicken wire, so mesh dishes, quite cheaply constructed. As you can see here, there's some poly tubes that act as ridges to give it a bit of structure, and then it's strung up between telegraph poles that are embedded in these concrete supports, just in this corner of the desert. And essentially, these things are drift scan. This is a drift scan telescope, so it just stares up at the sky, has a particular field of view, and then all these dishes are closely packed together in a mostly hexagonal pattern. So we have lots and lots and lots of copies of similar baseline lengths. So the shortest baseline length between these two dishes being about 14.7 meters, we have many, many, many copies of that short baseline length. The reason it's set out in this configuration rather than a more scattered configuration that interferometer people might be more used to is so we can do redundant calibration. So by measuring effectively the same mode in the UV plane again and again and again with many, many pairs of dishes, we try and use that to get a relative calibration, and then that leaves only a few additional modes that we need to additionally use a sky model for to get an absolute calibration. So this is all built to be redundantly calibratable. So all these antenna elements, these dishes, these baseline lengths should be as similar as possible, as I'll mention briefly in a little bit. And this is something Samir and I worked on quite a bit. They are not perfectly identical. There's some non-redundancies that present a challenge. But by doing this, we're trying to get a good relative calibration between all of the baselines. And ultimately, this will be about 350 dishes. They're pretty much all built, but not all of them are instrumented. So I don't know if you can see in the picture here, there's these strange-looking metal, they almost look like Christmas decorations to me. Those are some receiver elements, which cover, I think on the next bit, I've got some specs actually. So they're dual polarization receivers, and the new ones cover approximately 50 to 220 megahertz. So that covers what we think is most of the EoR, most of Cosmic Dawn 2. And going to 50 megahertz means that in principle we should be sensitive to the range where the edges feature, the edges dip is seen as well at 75 to 80 megahertz. Because it's a drift scan telescope, it's just pointing up. We're only sensitive to a particular stripe on the sky. So here you can see this is just plotting right ascension and declination. And because of where we are on Earth, we're sensitive to about DEC of minus 30.7 degrees, plus or minus the width of the beam, and that's the stripe you can see here. So it covers areas that do cut through the plane of the Milky Way, but we also have some nice quiet regions. We've defined different fields here, field 1 to field 3, depending on what's going on with the galaxy. Obviously, you'd rather be somewhere where there isn't much galaxy, because that's one of your brightest contaminants, but you also want to be somewhere near to a calibration source so you can do your absolute calibration. So I'm not going to talk about that too much, but please ask me if you want more details. One thing I will point out is that you can just about see there are some nearby bright sources here. I think that one might be Fornax A, but don't quote me on that. Very bright, quite complicated, so spatially complex sources, quite close to the field. If Fornax A wasn't there, I think we would have used this field between F1 and F2, but as it is, Fornax A is in our side lobes, and it's kind of nasty. So lots of interesting problems like that go into how we've selected these fields. We did a couple of initial seasons of data acquisition. This was actually using just a small corner of the array that had already been constructed and instrumented with the old receivers from the paper array. So this is before we had those nice Vivaldi feeds that I showed you earlier, So we're using the old paper receivers just to get up and running. So they have a slightly narrower bandwidth. They only cover about 100 to 200 megahertz. Although still that's a pretty good redshift range for us. We focused on 3 clean fields, the ones I've just shown you, where clean means lower foregrounds, but may also mean less affected by RFI, less affected by bright sources in the side lobes. And in this configuration, what we call the H1C configuration, we got data from 39 good antennas out of about 52 that were instrumented. So you can see those here. X-axis is east-west position of the antennas. Y-axis is their north-south position, relative to some array center. And anything that's a white color, those were good antennas. And then any other color means that those antennas were fully flagged due to either the antenna being a bit screwy, so that's the blue ones, or having struggles calibrating them, which may be due to instrumental issues or otherwise. Those are the ones that kind of pinky orange color. But all the same, we got about 18 nights of good data from a few years ago, so mostly through December 2017, which of course is Southern Hemisphere summer. And with these data, we did a full redundant calibration. So we did a relative calibration of all the sets of baselines. So again, remember that. So let's look at antennas 12 and 13. That's our shortest east-west baseline. There were many copies of that east-west baseline with a similar length. So we did a full redundant calibration of all the available redundant baselines, sets of baselines. And then, as well as that, we did a partial absolute calibration, because you can't solve for every single degree of freedom in your gains by doing a relative calibration. You need some absolute scale as well. So we did an absolute calibration based on a sky model of those 3 fields when they were close to a somewhat bright calibration source. So that would be a calibration source that's a few Janskys rather than really bright and spatially complex source like Fornax A. So again, there are details in the paper if you're interested in that. We subtracted cable reflections. So in the receiver chain, we did see some reflections between the different elements. They scattered power outside that foreground wedge. So we had to subtract that power. And we did that by fitting quite a simple model of the way these reflections could affect the gains, and essentially treated it as an additional gain calibration. And that seemed to work quite well. But the regions where those cable reflections have affected, we're still treating cautiously. So, regions in 4A space there. And as I already mentioned, we're doing foreground avoidance. So we're not trying to measure anything inside the foreground wedge. We're only looking at modes outside that wedge. I just want to give you an example of this cable reflection systematic. It might be a little bit hard to see here, but along the x-axis, you've got K parallel, so that's your delay mode, the Fourier transform in the frequency direction, and this is a before and after as a function of time, so local sidereal time, which you can translate to RA if you want to. And in the middle, you see the bright foregrounds. This is for one particular baseline I'm showing you here. You can see the bright foregrounds, and mostly within this low delay, so low K parallel region, but then you have these faint streaks at K parallel of about minus 0.6 and plus 0.6. There's a bit of structure in there. Those are the cable reflections. So ultimately, we fitted those out using what ends up being a 28-term Fourier series, and you can see they look to have been well subtracted. I can show you another plot on the right-hand side here of the data with this cable reflection in for a particular baseline. So you can see there's lots of other structure as well due to what we think of mutual couplings and things like that. We try and fit those out, and this is the residual you get. So within this region, out to a delay of about 1500 nanoseconds, you had to do quite a bit of subtraction. Again, we think it's a well-posed subtraction, and the model we've got isn't going to dramatically overfit and cause signal loss or anything like that. But we still treat it cautiously. You can see outside of about a delay of 1500 nanoseconds, The model isn't doing much at all, which is good. We don't think we have cable reflections there that we need to be worried about. But this was one of our main systematics. Yeah.
So what is?
Go ahead.
So what is the frequency you are referring to?
With the particular frequency band. So I think in this one, I didn't put it on the plot. This will be, I think, the higher band, which is roughly, I think, 160, 165 megahertz, about a 20 megahertz band. We have two main bands that we're looking at, which are kind of the frequency is just above a very bright communication satellite, Orbcom, and just below that. So they were the most RFI clean bands. Sorry, I should have put a plot of the bands on as well. That would have been useful information. But that's roughly the spec as I remember it. I can look up the actual numbers if you like.
Yeah, thanks. Yes.
No, great. So yeah, this was our one of our main systematics for this analysis. With the new receivers, those Vivaldi type receivers, there's been a big suppression of any cable reflection systematics. So we're doing preliminary tests with them now, but we think certainly cable reflections of this sort of size, this big green bump, I believe we're not seeing anything as large as that. So the new receivers have nicer characteristics in terms of suppressing reflections. Instead, we'll be more worried about things like mutual couplings between the antennas. That will be an issue for us instead, I think. So, of course, then we take these data, we run it through our pipeline, we do all this calibration, systematics cleaning, various binning, lots of cuts to get rid of residual RFI or days that couldn't be calibrated well or things like that. And then we put that through a power spectrum pipeline and measure power spectra, and that's how we derive our upper limit in these redshift ranges. Now, we don't just do that, of course. We do lots and lots of statistical tests on the data to try and understand the data quality and whether the thing we're measuring is actually an upper limit on the 21 centimeter signal or we're just measuring systematics. And in this analysis, what I can actually say is so far so good. It looks like we do have some residual systematics, but the data are integrating down in a mostly noise-like way, which is exactly what you would want in this regime. So we know that we don't have the signal to noise yet to detect where we think that the actual 21 centimeter signal is. So we're just hoping we've got a nice clean signal that's just very noisy, and as we integrate down, the signal to noise will improve. What you can see here, the bottom right, these we call them Allen variance tests, although they're not really that. So we're essentially integrating over baselines for one particular baseline group, say, and we're taking the average of the power spectra, the cumulative average, sorry, as we add more and more data, and it should integrate down like 1 over n. Essentially, the noise level should reduce, our signal to noise increases. So the theoretical, just to guide your eye, that this has an arbitrary normalization, but the theoretical behavior should be this black dashed line. And then when we average over absolutely everything outside the wedge, in our clean region of Fourier space, the yellow line is what we get as that cumulative average. If we were seeing lots of systematic effects, that would deviate quite significantly from this black dashed line, we think. So we see there are some deviations from the line, but at the moment they're not particularly significant. So they're still consistent with noise. You can see on the right we've got a noise-only simulation, and you do get small deviations from the black dashed line, just stochastic deviations. But we do perhaps start seeing some hints of detecting what we would assume is a systematic here. So it's beginning to deviate away from that ideal behavior. So we know there's more systematics in there. We know we have to do better with the calibration. We know we have to do better with things like RFI removal and things like that. But as an initial analysis, we're pretty happy that we've controlled our systematics well enough to support the upper limits that I'll present in just a second. I've also shown here a representation of the level of non-redundancy We're using this redundant calibration strategy, but the antennas, the dishes, the baselines aren't fully redundant, so that causes a model error. And Samir is actually one of the people to talk to about that, because he's been working on that stuff, but I thought I'd just mention it here as an example. So by no means a perfect analysis, but we think we've got pretty good control over the level of any spurious effects that could be causing us problems. Okay, so I'll just very briefly show you our preliminary power spectra. So these are, in fact, this paper has now been accepted, so I can actually remove the preliminary tags here. It's just been accepted. So here you can see this is our 1D averaged power spectrum. We've got K along the x-axis. This is the shape of the window function in each band power, and the pink lines are our band power with error bars derived through a variety of different ways. We put quite a bit of effort into figuring out the proper way of accounting for the uncertainty. That's largely thanks to Chanrong Tan, who's in UPenn, University of Pennsylvania now. And you can see here that this black dashed line is what we would expect if we just had pure noise, so no signal detection. The power spectrum we get just with pure noise, and then the pink points are our actual measurements, and you see it's pretty consistent with noise. So this just backs up the thing I would say. We think we have a pretty good, pretty robust upper limit here that isn't just a measurement of some systematics at high signal to noise. What does this mean for physical scenarios? Well, our upper limit is I think pretty much the best at this redshift of about 8. So again, I can now remove these preliminary tags. These two pink points are our two different bands. So we've got one measurement at a redshift of about 8, another at a redshift of about 10.4 central redshift. And you can see various other experiments plotted on here. And this is the delta squared power spectrum here. So you see at this redshift of about 8, we currently have the most stringent upper limit with this data set. Which is pretty good. And when you put that into 21cm fast or one of those codes to try and constrain physical scenarios, it just very slightly improves the constraints on more exotic scenarios. You can see a few examples here of these black lines down here of possible 21 centimeter signals that you might expect in a few different a few different scenarios, essentially. So it's progress. It's progress compared to the telescopes that went before us, some of which are of course still operating. But we've still got, that says 10 to the 3, this is 10 to the 1. So we've still got at least 2 orders of magnitude in power to go, which means we better be taking more data and doing a better job with our calibration, which is very much the focus at the moment. So we already have a factor of 6 to 7 times more data already on disk, analyzed, reduced, calibrated. We're doing power spectrum analysis on that now, so we'll hopefully have results for that out hopefully early, maybe middle of next year. So with that roughly 6 to 7 times larger data volume. So that might move this point down slightly, but it's all progress. Just to give you a few more specs of what's coming next. So this is still with the same receivers, those older paper receivers that have now been replaced, but it's a much longer set of observations now between October 2017. Remember, the previous ones were December only, all the way to the end of March 2018. So we've got better calibration, better RFI flagging. We're doing more filtering and weighting to try and deal with these systematics. And when all is said and done, we would naively expect about a 5 times improvement in sensitivity. But the one to really watch out for, and that's probably on a kind of 1 to 2 year timescale for an initial analysis, is using these brand new Vivaldi feeds and way more dishes, so the full array of 350 dishes. And we may even be able to reach the edges band, depending on how well we can calibrate that frequency range. And this is, I stumbled across HERA on Google Maps. There's up-to-date satellite imagery, and this is what HERA looks like as of a couple of months ago, I think. And so you can see each dish here, and they're all hexagonally close packed, but with this break in the middle, which is just to give a bit more variation in the number of baselines of different lengths. And as you can see here, that's looking pretty complete now. You can just about see an outrigger dish there. So not all of these dishes have been instrumented yet, but we're well on the way to that. So I'm quite hopeful for the near future. We'll have a much more sensitive telescope, and I'll hopefully be able to present some results in a year or two, which really move the dial on that power spectrum upper limit. So I'm conscious of the time. I'm going to try and talk about MeerKAT a little bit. I'm also going to briefly advertise some of the HERA software we have here, but please do give me a 5-minute warning or something when I need to wrap things up. And
Yes.
Yeah, thanks. So the HERA pipeline is actually pretty much all open source. We've actually, me personally and many others, have spent quite a lot of time on the software, and not just writing it, also testing it, and there's even a bit of documentation, which is slightly shocking still in this day and age that there's not more documentation. But we're on a good trajectory with that stuff. So what do we have that may be useful to other people? Like I said, it's all open source. You can use it freely for anything you like. I think one of the most powerful packages is HERA-Cal, and that's our code for doing redundant and this partial absolute calibration. So if you have an array that has any level of redundancy, HERA-Cal should solve pretty much most of your use cases if you want to do a relative calibration. But we also have a CASA imaging-based absolute calibration segment to that. Although again, most people are happy to use CASA for absolute calibration anyway, so we don't add much on that side of things. One that I've been personally quite involved in is the power spectrum estimation pipeline, and particularly this software package HERA PSpec, which is an optimal quadratic estimator-based power spectrum code. And it comes with various convenience functions for plotting and storing the power spectrum data and stuff like that. So I think that one's definitely worth a look if you need to calculate power spectra. We've got a visibility simulator, which myself, Samir, and a number of other people at Queen Mary have been putting a lot of time into, making it much faster, making it more accurate, things like that. I think it's now quite a nice package for doing visibility simulations, and we've got this pipeline that in a pretty automated way, and it's parallelized as well, can do gain calibration, a very simplified form of absolute calibration. It's hard to do that in an automated way, but we've got a very simple thing there. And then power spectrum estimation. So you can study things like systematic effects, and you can get the code here. And I'm just showing an example here of a wedge plot, so 2D power spectrum, where we added no perturbations to the beam. We perturbed the beams, and then this is the difference between them, and you can kind of see the size of the effect that you get when you add that particular systematic. And so Samir led this nice paper here that's now published, where you can find more details of that. But I guess open source, and you can just download it and hopefully run it and just tweak a configuration file. And I'm very hopeful that this will be a fruitful avenue for our master students to get started with radio work, radio interferometry, without having to write their own pipeline from scratch or learn CASA in great depth. So first results from MeerKAT. Because of the time, I'm not going to spend too much time on this, but I do want to show you this other side of things. Oh, go ahead, Samir.
We have 5 more minutes, yeah.
5 more minutes. Okay, great. So as I've already mentioned, MeerKAT is this SKA precursor, SKA mid, so mid-band precursor, with receivers in the kind of 1 gigahertz region. It's 64 dishes. It's on the same site as HERA, and by all accounts, it's a fan exceeding its design specifications in terms of sensitivity. And some folks have done an amazing job with it. So the band we're actually using is the L band. That's 900 to 1670 megahertz. There's a UHF band fitted too. The receivers, so they're actually 23 Kelvin, and you can degree each of these as dual receiver. And as an interferometer, for our purposes, is for sensitivity reasons. So the array is too sparse to do a good job ping with as an interferometer. Plane is too sparsely covered essentially, but as single dishes you can use it kind of like a CMB experiment and scan across the sky and build a pixel, and all our forecasts suggest that that should work reasonably well if we get the observing time we want. So there's this class survey proposal to do a 4,000 hour survey covering the DES footprint. So we've done a Pathfinder survey though. So we did about 10 hours on all 64 dishes over the Wiggles Galaxy survey, 11-hour field, 3 by 30 degree stripe. We used noise diode fires, so periodically we fire a noise diode into the receiver to do a kind of temporal relative calibration. I'm always happy to talk about that at the moment. Frequency versus just a raw unnormalized signal. We have tons of RFI in this band, so even this very, very, very radio quiet, legally protected preserve in the middle of the desert in South Africa has terrible RFI, but we have a couple of clean windows, which is what you can see shaded in white here. Scan strategy, so RA and DEC along the X and Y on the top here, and depending on whether the field is weak, to avoid adding ground spill, we just had some time dependence due to ground spill by sticking at constant elevation, and we just scan the sky like this in this nice cross pattern, and we can actually build up pretty good maps from that. And then on the bottom here, this is just showing you our noise diode fires. So the noise diodes are on for essentially every 20 seconds or so, and we use those to do a relative calibration. And then here's the map, or the maps, because of course we're doing this over many frequency channels. So top, you can see a galactic model. That's just based on other data, things like the Haslam map, the Planck and WMAP map, stuff like that. In the middle, you see our measurement now, the calibrated data. And shockingly, they look kind of similar. We're very, very happy with this. The 0 point isn't exactly the same, but you can see a lot of the structures are very similar. You can see fainter regions here and here, brighter regions here and here, and then in pink are things that aren't in the sky model above, which are point sources. We find where the point sources are, which is pretty good. When we subtract the two, we get this residual, and you can see the red blobs mostly correspond to point sources that weren't in the model, although there are some fluctuations, some diffuse fluctuations as well, because the sky model and our calibration aren't perfect. Using this technique, which is really promising for SKA, because we would want to use the full set of SKA-1 mid receivers in a similar strategy to be able to make maps in this way too. Again, just as more proof that we have actually been able to calibrate this telescope despite this not being a supported design mode. Here's a map of the 21 centimeter line from the galaxy, just in quite a narrow band. So the white contours that are overlaid are from a measurement using the Effelsberg Bond telescope, I believe, and the color map is our own measurement. And again, you can see recover the structure and have a sensible calibration, even for quite narrow bands. I'd better wrap up, so I'll just very briefly mention a couple of this. We foregrounds, and particularly measuring the SCDs of the foregrounds using this TT plot method. Mel Irfan at UWC has been leading this, and we've been using this to try and measure the curvature of the synchrotron spectral index. We have a pretty good initial proof of concept measurement of this, so you can read more about it in this paper here. And the main aim of this is ultimately to try and measure the baryon acoustic oscillations, which again, I'm sorry, I'm going to skip over this, but please ask me more about it at the end or otherwise. But we've been, hey, there's me, Samir, and PhD student Fraser, who critical aspects of this and how best to measure the BAO, even though we have limited angular resolution. And then I'm going to skip over this stuff and just mention we've already started a 100-hour observing program, or what we hope will be about 100 hours, cross correlations with the Wiggles survey to try and detect the 21 centimeter signal at low redshift in cross correlation, but never with so many dishes. And we already have pretty nice spectra of the galactic synchrotron that might be interesting to foreground people. And this is all, again, in the context of making iterative improvements to the calibration. I also want to advertise a simple simulation code that I've been working on here called Fastbox, which, if you're, again, trying to study systematics and foreground removal and stuff like that for these lower, that should be pretty great. Thank you very much for your attention. These are exciting times for 21 centimeter intensity mapping. We're almost at the level of having the raw sensitivity we need to actually detect these signals. There are still tremendous analysis and systematics challenges, but we're chipping away at them. And I'm very pleased to say that the experiments I'm working on are doing well, and we'll hopefully be getting ever closer to a positive detection very soon. So again, thanks for your attention, and I'm happy to answer questions if there's time.
Yeah, thanks, Phil. Yeah, so for a nice talk. So now the time for a few questions. Please unmute yourself and ask questions. Yeah.
Phil, So this cable reflection you mentioned, that signal is reflected at around K is 0.6. So why it is so?
Yeah, I'll flick back a few slides. Sorry for the, oh, I went too far. There we go. So it's essentially down to the length of the cables. So it's just a light travel time down a cable and then back again. So, don't test my mental arithmetic right now. But one of these features corresponds to, I think, a 50-meter cable, and another one might be a 200. I'd have to do the maths, but they quite closely correspond to particular cable lengths in our receiver chain.
So that's not broadband. That's more or less narrowband signal, kind of.
Well, the signal that's actually reflected is the whole signal over all frequency channels and the whole sky. So, kind of what we see is a reflected. So this green bump here is a reflected and attenuated version of the foreground bump here. But it's restricted to a narrow range of delays, just because the signal reflection thing you get is essentially, you get a time delayed copy of the signal. Mm-hmm. So that's why it appears as a narrow feature in delay space. I don't know if that's what you're asking.
Yeah. Thanks.
Do you have any other questions? Please unmute yourself and yeah.
I'm also very happy if people have questions to, just email me. I know that was quite a large amount of information in a short space of time. I'm happy to give you the slides to keep or email around if that's helpful as well.
Yeah. Thanks. Yeah.
So maybe I can ask one more question.
Yep.
So HERA also covers the edges band. So you have any observation in that band now, or?
Yes, but there's still a preliminary stage of data reduction. So that's only with these newer receivers, these Vivaldi feeds. The old paper receivers don't go down to such low frequencies. But yeah, so that's a data set we call H4C for some reason. But that's currently being analyzed. We could look at the power spectrum in that band already, but we wouldn't trust we wouldn't even trust our calibration enough to do that internally yet. So, Samir has actually been one of the people working on that for a little bit, right, Samir? I don't know if you have any.
We did some of them, but still we need to make some final, yeah.
But yeah, so hopefully within I'll hedge my bets and say 1 to 2 years, we will hopefully have some upper limits in that range. I don't know how useful they'll be for checking the edges signal. Eventually, I hope they'll be very useful, but we'll hopefully have initial results soon.
Okay. Yeah. Thanks.
Any questions? Last. Okay then, so thank you all, and thank you Phil for giving me such nice talk. So also Phil will be available via email, so if you have any questions, please send him. Okay, thank you Phil, yeah, and thank you all for attending this colloquium series. Thank you. Okay,
yeah,
bye.
Thank you Phil. Yeah.
Thanks. Bye. Take care.
Bye.